All right, we are going to work on describe quadratic functions. So now that we've learned about quadratic functions, we've learned about the shapes that their graphs take. You can see, you can tell just from looking at the pictures which ones here have to be quadratics and which ones don't. I'm not going to tell you how. I think these are very simple. We have learned so far about linear functions and exponential functions. And I'll remind you that exponential functions have a curve in them, but they also have they have a feature that is basically like a little tail, right? And I'm not going to tell you what it's called. I think you might remember, but I want to see if you can remember that, and I'll ask you about it later. Okay, but basically they curve either into this tail or they grow out of it. So we have growth and decay from this tail. I'm just calling it a tail. That's not the real name for it, but we already talked about that, so I think you should, at this point, already be able to do that. And then quadratic functions have their own shape. So by now, you should be able to recognize the shape, and I'm not going to show you that right here. The next thing is that we know quadratic patterns have symmetry. So use your symmetry checks to see. And the only other thing is that you definitely need to know your perfect squares. So let me make a little reminder list here of perfect squares. So I'm going to spend just a second and remind you that quadratics, which are the patterns of squares, so we're going to look at perfect squares. So remember that we start by measuring things on a ruler, right? If I was to take a ruler, all right, I think I can just measure 1 unit from here, from here to there, about 1 unit, right? And then if I turn that 90 degrees, I can make a square that's about 1 unit right there, right? So from here to there, and then I'm going to get that guy out of the way. So if this is 1 by 1, that is what we call 1 square, and there is 1 square unit, so 1 unit squared in there. But if I was to double that and go 2, right, which would be like 1 here and 1 there, right, and then make a square out of that, right, so 2, then what we would have is we would have a 2 square, and it would create 4 units squared, right? If these are centimeters or whatever, right? I'm going to get that guy out of there. Okay, so now what if I did it with 3? All right, 1, 2, 3. And then if I made a square, 1, 2, 3, right? That's not a very good square, but you get the idea. Then this would be a 3 square. 3 square, which would give me 1, 2, 3, 4, 5, 6, 8, 9, which give me 9 units squared. And by now you know a 3 square, you can find out the number of units inside by taking whatever the length is, right, and multiplying by whatever the width is. Just like any rectangle, a square is just like any other rectangle. And they're fancy, they're special because each side length is the same. But that's how you can find it. So when I go 4 squared, well, I know I can just say that's equal to 4 times 4. That makes 16 units squared, right? I don't actually have to draw it all out. And so we can now get very generic about it and say, hey, these aren't even necessarily squares. Just if I make a square out of 5 squared, I can just call it 25, right? 5 being squared will give me 25. 25 what? Well, they're 25 units squared or whatever. 6 squared. Okay, 36. So if I keep doing this, 7, I'm going to find this pattern. Here it is. Ready? 0 when I have length of 0. Then we had 1, 4, 9, 16, then it goes 25, 36, 49, 64, 81, 100, 121, 144, 169, 196. Ooh, boy, 196. I started thinking ahead, 225, and then that's enough. So this pattern here, sometimes if you ever see these numbers in that order, you should be thinking, hey, man, I recognize my perfect squares. These are called the perfect squares. So sometimes we can recognize quadratics from symmetry, because they will have symmetry. And you might be saying, where's the symmetry here, Mr. T? Where's the symmetry? I only just see numbers going up. I don't see the symmetry there. Well, where the symmetry comes from is this. Watch this. If I were to do this, oh boy. Oh, whoa. My fingers getting things out of control here. Let's try this again. All right. If I were to make these same squares, but I were to go in a negative direction, right? Let me do this with another color here so it stands out as negative. Here we go. So if I went instead of forward into the positive, what if I went backward into the negative 1 unit, right? That'd be negative 1 unit backwards. And if I squared it, instead of going, I don't know, I guess I went down already, but pretend that was 1 up and 1 over, right? Positive. Now if I go negative, I get negative times a negative, but how many squares is that? That's still 1 positive, because negative 1, if I make a square out of negative 1, it is equal to negative 1 times negative 1, and that's going to give me an area of 1 unit squared. Hey, that's the same number that I got right here. So negative 1 times negative 1 is 1. So there's my symmetry, negative 2, if I make a square out of negative 2. Now be careful, you can't write 2 square that and then make it negative, because then it'll take this, make a square out of this, and then make it negative. So we don't want to do that, right? Let me get the eraser over here. Boop. Okay. So what we want to do is we want to make a square out of negative 2, which is negative 2 times negative 2, which would give me positive 4, and there's my symmetry again, right? And the same thing would happen. So my symmetry comes from making squares from negatives that are going to be identical to these positive squares. So anyway, this is your list of perfect squares. And at the very least, you should try to remember these first ones. 0, 1, 4, 9, 16, 25, 36, 49, 64, 81. Try to memorize those first ones. If you can get all the way out to 225, good for you. Good for you, okay? There's nothing wrong with that. Learning how to do those, connect those, and memorizing them. So that might be helpful for you somewhat in there. And now you have these in table forms, and you're looking for symmetry or perfect squares. And here again, you have another level where you're doing the same thing. You're looking for symmetry or perfect squares. Okay? And now we have this. This is what I really want to spend some time on. I am going to, I don't know, pick one of these, okay? I'm going to, I'll do this one. I just don't know why I'm going to, so let me do this. Let's see. I think I can do this right here. Because these can be kind of tricky. Kids can read these and be like, I don't know what that means. So, and I don't blame you. It's tricky. You got to have some practice. I'm going to try to introduce it here, and then we'll do some practice with these later on, okay? But when I read this, it's wanting me, see what it says. It says, write a function, make its graph and table with 5 values for the pattern. So this is a pattern. Now the pattern begins with the square. that increases its side length and one side by 4 each time. So in other words, if I started with a square that was size 1, right, it'd be 1 by 1. And then if it became 2, that would measure 2, right? 2 by 2. But that would be my first increase, right? From 1, it increased its side length from 1 to 2. But notice it says, and one side by 4 each time. So that means in addition to the 1 becoming 2 here and here, I also have to add plus 4 more here. So this is going to turn it into a rectangle. So a 1 by 1 would be 1 times 1. A 2 by 2 would be 2 times 2. But actually it's 2 plus 4 times 2. The length is 2 plus 4 times 2, right? And then the width, here we go, I got 3 times 3. What am I adding in here? Plus 4. So I've got this rectangle. So the square is getting bigger from 1 to 2, from 2 to 3, right? And then one side has an extra 4 added in. Okay? So if this pattern kept going and I wanted to describe it, I can't call this 1, I can't call it 2, and I can't call it 3 because that's changing. And anytime there's something that's changing, if I'm changing the length, I have to use something that varies or changes. This word vary. To vary something is to change something, right? And this is something that changes. It's called a variable. A variable. Oh, it won't let me draw because this, how do I get this guy out of here? Come on. Does it just go forever? What's going on here? Sorry, man. I don't know where the end of that ruler is. It looks like, oh, I think I just click on it. There it goes. It goes away. Sorry. So anyway, it is a variable, right? So this side length is a variable, right? And what's this side length? Plus 4. It is the same variable. So I could describe a square that side lengths keep changing as x squared, right? But in this case, with this pattern, the side length, which I'm going to call x, has one side is going to be x plus 4. So what's this pattern? It is length of x, width of x plus 4. So I would write it as x times x plus 4. Okay, that's my answer. That's the function I would write. I would say f of x equals x times x plus 4. And if I were to turn that into a quadratic function and I wanted to find the area of that rectangle, I would then think about distributing here, right? X times x and x times 4. So that area of the rectangle would be x squared here, x times x, plus 4x more. That's this rectangle down here, 4 times x, right? Oops, 4 times x. So I could write it as x squared plus 4x. These two are the same function. So f of x equals x squared plus 4x. So now I can go to my calculator and I can graph that function. Here we go, start over, get a new document, put in a graph page, put in x times x plus 4. Oh, it doesn't like the x times unless I put a times in. So I got to hit the times button. Otherwise, it's like, wait, what is that? So there we go. And here's my parabola. So now it said to me, make its graph, right? So I'm going to draw a graph. So my graph looks like it goes through the origin, comes down here, and goes back up. So I'm going to make a sketch of that. So So if I wrote my function out, let me answer this question. The answer was f of x equals, you know what, hold on. Let me get this a little bit bigger so you can for sure see it in the classroom. F of x equals x times x plus 4, one side and another side. The sides are each growing, but one side is growing by plus 4 each time. Okay. And then the graph has a parabola that goes down like this and goes back up, kind of like that. And that's not a great looking parabola. It's not perfect, but you get the idea. Looks like it goes through the origin. Probably I could do it. Let me try. I think I could do a better job than that. Let me try that again. Here, let's see. Get my marker back. Okay, here we go. So a y-axis, an x-axis, and then I have a vertex right here that kind of goes up like this. And since it's a vertex, I got to make it curl and look like it has symmetry. So it's something like that. So there's my graph. I could show that as my graph, right? And now I need the table. And here's a trick, right? Control T. On these calculators, you can press Control T. And there's my table. And I think what I'll do is I'll just include, it says include the first 5 numbers. So 0, 1, 2, 3, 4. That's 5 numbers there total, right? Because 1, 2, 3, 4, and 0. So I would write it like this. X, f of x, the function's value, which depends on x, and the input x. 0, 1, 2, 3, and 4. And I can use this right here to do it. 0, 5, 12, 21, and 32. So there they are, right? There's my values. Okay? Keep going if I want, but I'm only supposed to have, look back at the assignment, it says write a function, or this level says write a function, make its graph and table with 5 values. So I just did that for this one. And what you need to do is recognize, how did I do this? What I did was I started by making the pattern, a square that is getting bigger, so therefore the side lengths have to be x and x of that square. And then it says, and one side by 4, so I added 4 to one side. And then I just renamed the growing square to x and x. And then I added in that one side plus 4. Okay? These are tough, I know. You got to kind of read through them and try to figure out what each one of these are and write their functions. The last one is level 6 is story problems. So maybe I will, I don't know. Maybe I'll do one of these right here. Let's do one more. And so here we go. I'll take this one about Alex. Why not? That's a good name. I've had many friends named Alex in the course of my life, and I'm going to make one more right now. Alex the gardener. He wants a garden. Okay. And it's a rectangle garden. So you know what I'm going to do. Your first job is always to make meaning. So I'm going to make a rectangle. It means 90 degrees right here. It says the length is 5 feet shorter than 3 times the width. So I don't know what that is. Let's just try. Let's call this the width, W, right? The length is shorter than 3 times that. So shorter than 3 times that. So what would that be? Here would be 1 times, that's a W here. The same, it's about the same length. I'm trying to make them about the same length, right about there. There's 1, there's 2, there's 3, right? So this would be a width, another width. So this is 3W, and this is the width, right? But it says it's 5 feet shorter. So if it's 5 feet shorter, well, what that means is I need to hop backwards, right? I need to come back minus 5. Okay? Now it wants a function that describes the area of the garden based on that width. And if I'm going to have to graph it and make a table of 5 values, then I'm not going to call this W. What I'm going to do is I'm going to call this, let's call this X. So this would be X, X, and X, or 3X minus 5. So here we go. I've got a function that says X times 3X minus 5. That is a rectangle that's length is 5 feet shorter than 3 times its width. So I started by making the 3 times its width and then made it 5 feet shorter, right? If I multiply, I can multiply this and I can find the area. X times 3x is 3x squared, and then x times minus 5 is minus 5x. I could do that if I wanted to, but I can also just put it in as x times 3x minus 5. So the function is f of x equals x times 3x minus 5. And now I can go in. That's my answer. I would need to go to my calculator now. Let's start this again. Menu. Let me go back to home and get a new one, not save any of that other stuff. Put in a graph and put in x times 3x minus 5. There it is. So there's my graph. I can make that graph, and I can also Control T my way to the table. Okay? So that's how I could actually make the graph the function and make a table and get all this done. So that is all the way through level 6 of Describe Quadratics. Okay? Listen, you got to get through these levels if you want to prove that you're earning your algebra credits. So I'm going to stop with the videos now and give you time to work. If you work really hard, you can get through these levels today. Okay, good luck.